Good morning, everybody. Welcome to Physics in the Universe, or good afternoon, depending on the time that you watch this video. This is going to be a straight run through. There's a class going on right now in the background. They're a pretty quiet class, so we should be able to get through this. So we're going over this Getting to Now video. Don't forget that as you guys are doing this Getting to Now video, that you're doing alongside this the Astronomy Beginnings worksheet. That's going to be due when we're done with this video. There's a question about when it's going to be due. It's going to be due when we're done. However, there's going to be a second assignment later on in this class where we're going to be doing something with retrograde motion. I'll explain that when we get to it. All right, so we're talking really about the history of how we've gone from most of our existence as being hunters and gatherers as humans to this modern society that we have now, where we had no understanding of what was going on in the night sky to, well, we have a lot of understanding today, but in the future there's even going to be more. So that's what we're working on right now. What have we already learned? We learned that this is not the moon. This is actually Mercury. And we watched a little video on Mercury. Mercury's first planet in the solar system. In the assignment that you guys are working on, question number 1 is going to ask you name the 8 planets in their order of their distance from the sun. So Mercury would be number 1. We talked about the ancient Greeks and how the ancient Greeks believed in a geocentric universe. So what is a geocentric universe? A geocentric universe is the Greeks looked up at the stars and they noticed that the stars seem to be orbiting the Earth. Now we know that better, right? We know now that the Earth rotates on its axis and the stars don't go around us. But they believed that the stars, the sun, the moon, and all the planets went around us on this great big thing called a... Anybody remember the name of it? Nope. This will be on the test, so be ready for this. This is called a celestial sphere. So all the stars were attached to this celestial sphere. All right. We also learned that there were 7 objects that were not attached to the celestial sphere that were moving what looked like inside of the celestial sphere, to which they called those 7 objects wanderers. It looked like the sun and the moon went around the earth in a perfect circle, but one of the things that were also noticed was that some of the objects, the planets, they seem to be moving independently. More specifically, not independently, but they have a strange motion in the background. So let me ask you this. Let me ask you this question. All right? Would it be weird if I told you that Mars comes to a complete stop, then goes backwards, and then moves forwards? Based on what you guys know about how planets move, would that be weird? Would that be a weird thing for Mars to do? You guys can nod your heads. I realize I'm on camera, so maybe you guys don't want to speak out loud, but at least nod your head. I've seen some people say, yeah, that would be weird. Mars is, according to Newton's laws that we learned earlier, the very first law says an object that's in motion will remain in that motion until a force acts upon it. So Mars, as is to the ancient Greeks, as it's going around the Earth, seems to stop, turn around, go backwards for about a month, and then comes to a stop, and then moves forward again. So I saw that look in your eyes. That's weird, right? But it totally does happen. So if you could imagine, if this is stars in the sky, all right, and we observe Mars, Mars would be here one day, and then another day, and then another day, And then what will happen is it starts to slow down. Every day we look at it, it doesn't go that far. And it's moving a little bit more east. And then it turns around and it starts to head back. And then it slows down and it turns around and goes back east. So if this is east, for some reason it turns around and goes backwards. It starts going west. Why that is? Well, it's something we're going to try to figure out today. Okay? I'm going to come back to that in a little bit. So keep that in mind. All right. Some Greeks rised up. Some Greeks are actually pretty smart. Because when I say the Greeks, I say that they believe in the geocentric universe, right? Well, not all of them. This man, Aristarchus. Aristarchus lived from about 312 to 230 BC. Remember BC, our calendar is based on when Jesus Christ walked the earth, so you can just think of BC as being before Christ. We live in AD, which is after death of Christ. It's not exactly what it stands for, but that's a good way of remembering it, all right? So when I say Aristarchus lived at 312 to 230 BC, just take 2023 and add that to 230. That would be 2,253 years ago when he died. All right. So he lived a long time ago. And he looked up at the night sky and he said, you know what? I kind of don't think that the planets go around the Earth. I think the Earth goes around the sun. Now, if you guys know anything about Greek mythology, does anybody remember the name of the god that carries the sun on his chariot across the sky every day, according to Greek mythology? His name was Helios. Helios is the god that carried across the sun. So when you see the word helio, that means you're talking about the sun. In fact, the word helium, the element helium, you know, the one that makes you talk funny when you breathe in a balloon, that comes from, the word helium comes from the word sun. All right? So heliocentric means sun-centered. So Aristarchus, now he didn't think that the stars went around the sun. He just thought that the planets went around the sun. And when I say the planets, the ones that you can see: Mercury, Venus, Mars, Jupiter, and Saturn. Okay? Does this catch on? No. In fact, later on in our story, we're going to find out it gets a little bit more tragic. When your country is governed by a religious institution, that means the laws are what's based on beliefs. And if somebody believes that the earth is the center of the universe, that means the law says you must believe that the earth is the center of the universe, even though today we know that completely wrong. You were told that it's that way around. So the thinking of Aristarchus never catches on because of this whole relationship between law and religion. Another guy, and this is kind of like if I were to have like some sort of like superhero of his time, is a guy named, it's pronounced Eratosthenes. And he's a little bit after Aristarchus' time. He is, God, he's smart. He says, I think that the earth is round. Everybody's like, that's crazy talk. The earth is flat. You can see the earth is flat. Look out there. The earth, it looks flat, right? Everybody believes that the earth is flat. But here's the deal. Eratosthenes, gosh, this guy's clever. Eratosthenes, who lives in, he doesn't actually live in Greece. I know it says the Greeks, but Greece, the Greek government kind of extended out to Egypt at the time. Eratosthenes lives in Egypt, in a town called Alexandria. Eratosthenes has a friend that lives really far south of Alexandria in a town called Syene. His friend writes a letter to him and says, once a year, the sun shines all the way down to the bottom of the wells. That's crazy, said Eratosthenes, because the sun never shines down the wells. It always hits at an angle. If you have a stick in the ground, it will always cast a shadow. But where his friend lived, the sun at noon would shine straight down. So what's the reasoning for this? Well, if this is the Earth, all right, one day out of the year, remember the Earth is tilted on its axis at about a 23-degree angle, all right? One day out of the year, if the sun's shining this way, like this, if you live right here, the sun is hitting you at a 90-degree angle. And this is called the Tropic of Cancer. Okay, does that make sense so far? So if you were building a well to the center of the Earth, your well, remember a well is where you get water out of, the sun would shine all the way down that well to the bottom. Does that make sense? If you lived up here and you built a well to the center of the Earth, notice that the sun, whoops, can't draw a straight line. Notice that the sun is hitting at an angle. So the sunlight would only go part of the way down the well. And that was his big aha. If sun is shining all the way to the bottom of the well in this place, but never where I'm at, that means the Earth must be round. But he takes it to the next level. He says, well, this is hitting at a 90-degree angle. It's a stick, and he measures the angle in which the sun is hitting the Earth here, and he finds out that it's like a 82.5 degree angle. Follow me so far here? That means if we drew a straight line all the way to the center of the Earth, what's this angle? Well, that would be 90 degrees minus 82.5. That would be 7.5. How many degrees are there in a circle? 360 degrees in a circle. All right? So if I take 7.5 and I slice it up, just like we would slice up a pizza, .5 slices, we would get, if you did the math, you would get about 50 slices. About 50 slices of pizza. Why is that important? Well, if you could figure out how far it was from this point, what's this distance? If you could figure out this distance from here to here, you could not only prove that the Earth is round, but you could tell me what the circumference of the world is. This is a little problematic because remember, we're talking about 194 BC, over 2,000 years ago. There were no cars, there were no satellites, there was no GPS. You couldn't just go for a walk on your app and it's going to tell you how many miles you walked. In fact, they didn't even have miles. Heck, they didn't even have kilometers back then. They had something I think they're called statutes, which is basically you would hire somebody, and this is what Eratosthenes does. He goes and he hires somebody. He doesn't do this himself because, gosh, that's a long way from Alexandria to Syene, to walk and count his pace. Count how many steps it was between the two cities. And there he had the distance, and he actually figures out how round the Earth is. So this guy at 194 BC literally figures out how far around the Earth is. And he's something like, it's like 13 or 15% off of what it actually was, which is pretty good when you hire somebody to walk from one place to the next. That you're only 13% off, that's crazy good. All right, so we have a video we can watch here. Hopefully it works. Probably have to watch an ad. How to fast track success.
Whether you're trying to get your ideas down,
of course it's Grammarly. It's always Grammarly.
It can be difficult to write.
I will point out that I tried to do my own account so we didn't have to watch commercials, but the school blocked my account. So.
Eratosthenes was a Greek mathematician and was chief librarian of the Library of Alexandria around 250 BC. He was also known as the father of geography. To calculate the circumference of the Earth, Eratosthenes assumed that Alexandria, the city he was in, was 5,000 stads, a measure of distance, directly north of the city of Syene. He also knew that Syene was on the Tropic of Cancer. On the Tropic of Cancer at noon on the summer solstice, the sun is directly overhead. This means that a vertical pole in Syene will not make a shadow. 5,000 stads north in Alexandria, Eratosthenes measures the shadow of a pole. He determines the angle of the sun by finding the angle the shadow makes with the ground. The measure of the angle of the sun is 1/50th of a circle. That's about 7.5 degrees. Zooming out, we see that the sun's rays come to Earth in parallel lines. Because the Earth is curved, the sun hits Syene from straight above and Alexandria at an angle. We use geometry to determine that 1/50th also represents the portion of the Earth's circumference covered by that 5,000 stads. So we can say that the circumference of the Earth is 50 times the 5,000 stads. That's 250,000 stads, which is about 46,250 kilometers. The real circumference of the Earth is 40,075 kilometers. So Eratosthenes' estimation is only 15% different. That's remarkable for 2,250 years ago.
Okay. Back to our PowerPoint. So, I mean, there's kind of the math behind it, but you saw it in the video, so I'm going to skip on to the next screen. All right, let's learn about Venus. First thing you might notice about Venus is that it's covered in clouds. You don't see the surface of Venus. Remember we talked about when we were talking about Mercury, and I like to use the moon here because the moon looks like Mercury. When we talked about Mercury, we said that, we talked about Mercury. We said that Mercury is the first planet next to the sun in the solar system, right? So you would think it's the hottest. And where the sun hits the surface, yeah, it gets hot, but it's not the hottest surface on the solar system. In fact, the side that's facing away from the sun is the coldest place than any surface on any planet in our solar system. Why is that? Well, the one thing that every other planet has that Mercury doesn't have is an atmosphere. And Venus, being the second closest sun, so it's number 2, so if you guys go to question number 1, the second planet you should have is Venus, definitely does have an atmosphere. And it's an atmosphere filled with natural carbon dioxide gases, along with volcanic hydrogen sulfide gases, and water vapor gases. But the water vapor gases, you would think, okay, so it has water vapor. Shouldn't it have oceans and rivers? Well, the problem is on Venus, it gets so hot that if there were any oceans or rivers, they immediately boil off. And why is it so hot? Carbon dioxide, water vapor, and hydrogen sulfide, hydrosulfuric acid, are 3 major greenhouse gases. What is a greenhouse gas? Well, it's like wearing a white shirt or a black shirt on a sunny day. Who's going to be hotter, white shirt or black? The black, because black takes in sunlight radiation and turns it to heat. So if you're wearing a black sweatshirt, I see several of you guys are wearing black today. When the sun comes out and you guys, about that time that you guys are going to be walking home, you're going to be extra hot because it's taking in that radiation and turning it into heat. White reflects that radiation, so it doesn't affect us. It doesn't create heat, I should say. Here on the Earth, we have a lot of oxygen in the atmosphere. Now, oxygen doesn't absorb radiation like carbon dioxide and those other greenhouse gases do. So as a result, we tend to stay cooler. But carbon dioxide gases are on the rise, and this is what's causing global warming. What is the worst case scenario? Why are scientists so worried about global warming? Well, we look at Venus and we see global warming going crazy. In fact, the surface of Venus is about, it's like 800 or 900 degrees Fahrenheit. That's the temperature on the surface of Venus. It's crazy hot. This is why, like Mars, we sent the little rovers to Mars to take pictures and dig in the dirt. We can't do that to Venus. I mean, the Russians tried to do that. They sent a little probe, and it landed on the surface of Venus, but it took about 3 or 4 good pictures and sent them back. But the probe melted. It's that hot on Venus. So how do we know what the surface of Venus looks like? So you can see in that picture, there's the surface of Venus. That's taken with infrared cameras, cameras that pick up heat, that can actually look through the clouds of Venus and allows us to see. And we find out that Venus has plate tectonics, just like the Earth, that it has volcanoes, very volcanic, just like the Earth. It's about the same size of the Earth, so it's typically referred to as Earth's sister planet. Now, one of the questions, I can't remember what question it is, ask you to tell me 3 facts about Venus. So here's a little video that you guys can watch.
Light oil change side.
Oh, it's not going to be Grammarly this time. And I don't know why it's not letting me go to full screen for whatever reason. And in fact, the internet's moving so slow it doesn't even want to play. Let's go. Try reloading. Oh, wouldn't this just be wonderful if we just stopped working?
Named after the ancient Roman goddess of beauty, Venus is known for its exceptional brightness in the night sky. But behind this facade is a world of storms and infernos unlike anywhere else in the solar system. Venus, the second planet from the Sun, is very similar to Earth from a distance, but up close, it's a very different world. Venus is about the same size as Earth, just slightly smaller. Its structure is also nearly identical, with an iron core, a hot mantle, and a rocky crust. The crust of Venus, however, is dotted with thousands of volcanoes, including Maxwell Montes, a volcano almost as tall as Mount Everest. Venus also has a thick, layered atmosphere. It's full of clouds that rain sulfuric acid and whip around the planet at speeds up to 224 miles per hour, faster than some Category 5 hurricanes. The atmosphere is so thick that it creates a surface pressure similar to what it would be about half a mile deep in the Earth's oceans. This pressure is heavy enough that a human standing on Venus's surface would be crushed. The atmosphere is made of greenhouse gases, primarily carbon dioxide, which create an extreme case of global warming. They trap the sun's heat, causing surface temperatures to rise over 880 degrees Fahrenheit, making Venus the hottest planet in the solar system. Venus is so inhospitable, neither humans nor spacecraft are able to survive the planet's surface. But some scientists speculate that Venus wasn't always so unwelcoming. From roughly 2.9 billion to 715 million years ago, global temperatures on Venus may have been just a few degrees cooler than Earth's are today. And scientists theorize that the surface may have contained shallow oceans that could have held enough water to support life. Today, life may still exist in Venus's atmosphere. About 30 miles up in Venus's clouds, where the temperature and surface pressure are similar to those on the surface of Earth, scientists have observed strange dark streaks that appear to be absorbing ultraviolet radiation, a phenomenon that could be evidence of microbial life. Life may struggle to survive in the atmosphere of Venus, but it is this unforgiving environment that's made Venus an icon of beauty. It reflects 70% of all the sunlight that reaches the planet, which is why Venus shines more brightly than any other planet or star in the night sky. While more than 40 unmanned spacecraft have visited this infernal world, Venus, so illuminated in the darkness of space, still has much to reveal.
All right, so you guys got your facts on Venus. All right, so you remember a little while ago I was telling you guys about Mars. Does this weird thing where if you look at Mars every night in the night sky, it'll move a little bit further eastward. And that makes sense because Mars is, we know, the ancient Greeks know. We know that Mars is traveling around the sun, just like we are, right? So it would make sense that every night that we look at it, it's in a slightly different place. Except, and this is the truth, Mars slows down, comes to a stop, then goes backwards. And then slows down, comes to a stop, and then goes forwards, back east again. So this is east, and for about 1 month it goes west. And the other planets do the same thing, then it turns around and goes east. That doesn't make any sense. If you think about how planets move, Mars is not going to stop, turn around, go backwards for a month, and then turn around, go forwards. But I'm telling you, this is what happens. And this perplexed those early people who were looking at the skies is why the sun doesn't do it, the moon doesn't do it, but the other planets, they all do it. And they couldn't figure out why. Well, this guy, Ptolemy, thought he figured it out. He said that the Earth was the center of the universe, a geocentric universe, that the moon went around the Earth, the sun, so this is the moon, the sun went around the Earth, that made sense, and every day as it went around the Earth it was going forward a little bit further east. But what about the other planets? Well, he explained it and he proved it mathematically that the planets went around the Earth, but like that, in spirals. Well, that would make sense, because every day, if Mars went forward every day, it's going a little bit further east, it's going east, it's going east, it slows down, and now it's going west, 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 slows down, and now it's going east again. Problem solved. Everybody believes in it. Ptolemy's model is accepted. Except that you guys should know better. Planets don't do loop-de-loops. If Jupiter did a loop-de-loop, it would literally throw all the planets in our solar system either into the sun or out into space. And there's just no way that a planet can do a loop-de-loop. So even though Ptolemy, who mathematically proved how the planets moved through the solar system, this is where the math teachers get mad at me. You could do math, yet still be wrong. all your math could be correct, but if you don't understand the mechanism behind it, you could still be wrong. And that's what happened with Ptolemy. Yeah, he mathed it out. And everybody believed him because he backed it up with math, but he was wrong. So what really happened, and this is a picture of what it was. What is this thing? What's going on? This is what he thought, that the planets were doing little loop-de-loops. This apparent westward motion of a planet is called retrograde motion. The explanation for it? Well, that's going to be today's assignment. You guys can find this assignment online. So I'm almost done talking here, but I can explain to you guys how to get to this assignment. For the spoiler alert, you guys are not going to see what the next slide's going to be. So go back to our page right here where it says retrograde motion. You guys everybody needs to open up retrograde motion. All right. I'm going to open up a copy of this retrograde motion. And what you're going to see is this assignment right here. Of course, as usual, put your name, date, period. It does actually go through and tell you what to do, and there's going to be some questions to answer. All right. I'll explain this code box here in a second. But what we're going to look at, I'm going to click on this picture. I'm going to hit Edit. I'm going to bring this up full screen. All right. And what you're going to see is the center right here, that's going to be the sun. This right here is going to be the orbit of the Earth. So this is where the Earth is in January. This is where it's going to be in February, March, April, May, June, July, August. All right? This is going to be the orbit of Mars. Simply what I want you to do is I want you to connect the January to January and see where it ends up with relationship to the stars. So how do you do that? There's two ways that we can do this. We can either do it this way, where I click the line. I'm going to just draw a line on here. All right. In fact, I'm going to copy and paste this line a few times because I'm going to use it. Control copy. Control V, 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 V. All right. Get rid of this line. That was an accident. All right, so I'm going to take this line right here, and I'm going to attach it. In this case, I'm going to attach it to February. See, it's attached to February, but I want it to go through February for Mars. So you can see what I did is I attached the line from February here to February in Mars, and now if we're on the Earth, in January, Mars looks like it's next to these stars right here. In February, it looks like it's right here. I'm going to bring me another line, and I'm going to bring it and go to March. And match it up with March. All right. So now it goes from January to February to March. And then we're going to do it for April, May, June, July, all the way to September. Don't worry about October. October was a mistake. I shouldn't have put that on there. But now you should be able to see how that planet progresses through the stars. All right. Then when you're done with that, you're going to hit Save and Close. And you're going to see, one more thing that you're going to do, I should probably do this, is you want to get the little scribble line. So you go to the line, scribble, and show me the path of Mars. What's it going to do? Is it going to go like that? We're going to see that retrograde motion. Right now you can see it's going a little bit further east each day. All right. So that's how you do it on the screen here. Some of you guys I know are a little bit challenged in using the computer. I got your back. I printed off a bunch of these sheets right here, which is the same picture. If you want to, you can use a ruler and a pencil and draw the lines old school style on here. The thing about it is, you're going to need to show me when you're done. If you do it on paper, I need to see that you have it done. So you're going to call me over and say, Mr. Lee, can you give me my code? And that's what this box is for right here. So if you do it on the computer like I was doing it, you don't need a code. The code is only for people who use paper. Okay? All right. So that concludes the video that I'm recording. So I'm going to hit stop recording now.